Hey guys, what's going on? So today we are going to be talking about an introduction to scattering. So scattering is the big topic in quantum field theory. Essentially, what scattering does, or what scattering is a way to calculate amplitudes that correspond to certain processes that involve the collision of two particles. Right? You might think, okay, two particles colliding, that's such a simple thing to understand. The particles, they come in contact with one another and they bounce off like two billiards. Well, it's not necessarily that simple. When we go quantum, what we're going to find out is that scattering is actually much more complex, and we're going to get deep into Feynman diagrams. We're going to dissect exactly what all these Feynman diagrams mean and the mathematics behind them as well. And so before we get into the topic here, what I want to say two things actually. One, make sure to hit that like and subscribe button. That really helps the channel. Two, I don't really like how the book lays out the rest of this latter part of talking about scattering. We're coming towards the end, the last maybe 100 pages in the book, and I think the organization is a little bit spotty. So what I'm going to try to do in the upcoming videos, or these last probably 10 or 15 videos. I don't know how long this is going to take. But what I want to do is I'm going to try to reorganize it a bit. Because, again, like I said, I don't really like how it's organized. But anyways, and I'm going to try to do it in a way that's easy to follow and that flows well. Anyways, let's get into the topic. Make sure to hit that like and subscribe button. All right. So you can see I have a blank page. Right? We're just gonna have maybe 3 or 5 minutes of just talking about exactly what scattering is, just so we can get our feet wet into this topic. Scattering, essentially, if we think of, we can think of a diagram where we have time. Actually, in most physics cases, we have space, actually, in the first dimension, or in a horizontal dimension. In our vertical dimension, we have time. Now, if you're not familiar with this, it might take a bit getting used to, but we can think of a scattering event as essentially two particles. They start somewhere. Here, I'll do this, two particles. So I'm going to have particle 1. It could be a boson, it could be a fermion, it could be any particle. Two particles at the same moment in time. So this is, say, time 0. I'll write the T down a little bit better. Time 0. Two particles start traveling towards each other, say. Or one might be still, one might not be still. They can't be completely still, right? Because you can't know the velocity and the position at precisely the same time. But anyways, I diverge. You have particle 1 moving, say, like this, and then, say, particle 2 moving like this. They get to some point, and something happens. Something happens in this black box. Right, this is a black box. We have no idea how these particles are going to interact with one another. But then out comes the particles again. Like this. And say we have our particles again. Right? So say this was particle 1. This is particle 2. This ends up being particle 2, and this guy ends up being particle 1. Say it was just a collision, like two particles collided with one another, like two billiard balls. Well, in that case, you have one collision, Actually, you know what? I'm going to reverse these, right? We want 2 to end up here. 2 and 1. Okay, well, one possible way... Actually, I'm not going to do that. If it was 2 billiard balls, the diagram inside the black box might look something like this. Right, where they don't actually, they physically bounce off one another. Right, so this is situation 1. And essentially, so we can think of maybe another situation, right? So I'll draw another situation. X and T, we have our 2 particles. We have our 2 particles. We have our black box, not our red box. We have our black box like this. And particle 1 is traveling this way, particle 2 coming in, and then we have, say, particle 1 here, and particle 2 here, so 1, 2, 1, and 2. In this case, our diagram inside the black box might have looked like this. They might have actually crossed at a point. And this crossing is an interaction. Something happened actually between the 2. They didn't just like bounce, but they actually engaged in something. And then you get 1 and 2 again. Right? There, you could get, say, a particle. Here's another situation. Right? We're going to come across a lot of situations in the book. We're going to say we have a particle, or 2 particles again. Black box. But I'm going to make this black box long. And then here, we're going to have our particles out here again. And say our diagram now looks something like this. Right, where we have 2 collisions, right? It's kind of hard to see, so we have 2 interaction points. Right, so in this case here we had 1 interaction point, and in this case here we had 0 interactions. But you could see that if we have particle 1 here, say this was particle 1, and this is particle 2, and this is particle 2. If we take this situation here, this one here, and we take this situation here, we can see similarities, right? One similarity is that we have 2 over here, 1 over here. Right? We have 2 over here and 1 over here. Right? And we start off with 1 here and 2 here, and 1 and here and 1 and 2 here. So the starting and ending points are the same. What happens in the black box, though, are 2 completely different processes. One process is literally just a bouncing, right? You have 2 billiard balls bouncing off of each other. Here in this process, you have two interactions actually happening between the 2 particles. And these 2 guys are known as vertices. And the idea here these are Feynman diagrams, if you don't know already. But the idea here is that the more vertices that happen in this black box, that is the higher number of vertices is associated with a higher order approximation. Okay? So you could have a black box, say, that looked, I'll just draw the black box. You could have a black box that, say, looks, so here's our black box. You could have a black box that, say, looks like this. Where we have 1, 2, 3, 3. This would be a third order approximation to some event in which 1 and 2 yield, let's see, if we follow these lines, we get, so 2 ends up here and 1 ends up here. Right, so that would be a third order approximation to something that would resemble a process that looks more like this, right, where 2 is over here and 1's over here. There are different locations in space, right, because this is the x-axis. So this process here is a third order approximation to a process that resembles something like this. This is the first order approximation, right? So the first order approximation is going to have somewhat of a higher precedent, but we don't want to ignore third order approximations or fourth order approximations. And the idea is that we put weights on the approximations so that we can understand exactly, not exactly, but so that we can take into account all of the potential processes that can take place between two particles as they go from their initial state to their final state, essentially. And that's essentially what we're going to be doing, right? And I'm going to do this in a way that kind of follows the book, but also kind of doesn't follow the book, because I'm not a huge fan of how the book presents Feynman diagrams and scattering. But we are going to come across a lot of very interesting notions. We've come across time ordering. We're going to go deeper into time ordering. We've come across normal ordering. We're going to come across normalization, or renormalization, which is placing a cutoff value essentially at high degrees of approximation, because this is where our summing of infinities is going to be a problem, right? We are going to come across regularization also, which is going to be important. And then we're going to dive into elementary models of our systems, right? We're going to understand what it means to consider scalar fields and Dirac fields and Prokop fields. And so this is where things get fun and interesting, essentially. And if you guys like this kind of content, and if you're ready to do some Feynman diagram calculations, then join me in the next couple of videos. And this is gonna be fun. So I'll see you guys in the next one. Bye.